Morning. So let's take a quick peek at our syllabus again. Okay, so you do have a test this weekend, or well, rephrase that. You have a test starting this weekend. So Sunday, it will open up. You'll also have Monday, so I'll be able to remind you guys on Monday. It's going to cover chapter 6, chapter 7, and chapter 8. So don't forget to take that or start that. We have already lectured on pretty much everything covered. We're just going to do some practice problems today with the limiting reactant stuff because those problems can be kind of time consuming. So okay. So here is a problem that I want you all to work on. I'm going to give you, it's kind of a hardy problem. So I'm going to give you about 15 minutes. We've got, well, let's do it in chunks. Okay. So I'll give you guys about 7 minutes to do the first part here, which is here's your balanced equation. And let me get it. So you have two known amounts. You have 25 grams of this KAUCl, and then you have 20 grams of that, and then you have 25 grams of the sodium carbonate. And you're working towards AuOH3, this guy over here. Okay. So I want you to tell me which, we'll do A, B, and C for right now. So which one is the limiting reactant? Which chemical is the excess reactant? And then how many grams of AuOH3 can you form? Or what's the theoretical yield? All right, so these three sort of play into each other. If you go for C, you'll be able to figure out what B and A is. You can just fill those in afterwards. So I want you to start going with that. Don't forget to use the balanced equation. And I am here. So please shoot me a question if you don't have no idea where even to start, because I want you to be able to use this time. Zoom in a tiny bit. Yes, I can do that. I just want to make sure that you can see everything though. Might be able to get away a little bit more. That's good. Okay, great, Leanna. So shoot to work on C, and then B and A will fall into place. Okay, just another minute to finish up your train of thought. Okay, so I'm going to work through these problems on another page. So let's see. So we have 2 KAUCl4 plus 3Na2CO3 plus, how many waters? 3 waters. Reduced to AuOH3, 6NaCl2. So it doesn't really matter that I write all the rest of these things, 3 CO2, but I'm going to fill them in anyway, plus 3 CO2. So this problem has given us two things. It says, hey, you have 20.00 grams of KAUCl4, and you also have 25.00 grams of Na2CO3. So we know something about this, and we know something about this. And the problem explicitly says to work towards the gold 2 hydroxide, which is this thing over here. So I'm going to have to go through two sets of stoichiometry, one to get my KAUCl4 over to the product, and another one to get my Na2CO3 over into the product, because this is apples and oranges. Can't really compare those numbers because they're two different compounds. Once I get them into my product, then it's much easier to see which one was the limiting reactant. All these other things that are in the balanced equation, we can just sort of, oh, not that one. We could just sort of ignore. It doesn't mean that they don't play into the equation, right? Those things are important in balancing and getting these correct coefficients. But as of right now, we can just sort of let them be. So this first one here, we have 20 grams of this KAUCl4, and your flow chart is always going to be grams to moles to moles to grams. Okay, that's how we hop when we're doing stoichiometry. We're in grams. So first thing is to get this bad boy into moles. So 1 mole of the KAUCl4 is equivalent to 377.9 grams. So this thing is heavy. Where did I get that? I took a potassium, a gold, and 3 chlorines. Now that we are out of grams and into moles, I can go from moles of this thing into moles of this thing. And I just use those nifty coefficients. In this case, it's a 2-to-2 ratio. So for every 2 moles of my reactant, KAUCl4, I will yield 2 moles of this product, which is AuOH3. That doesn't work for grams. That's not saying 2 grams of this, 2 grams of this. It's got to be in moles. From there, we're going to turn this thing, our product, back into grams. So for every 1 mole of AuOH3, this thing weighs 247.99 grams of AuOH3. So the moles of the reactant canceled, the moles of the product canceled. When I solve for this, I get 13.12 grams of the AuOH3. Now you're not done. You've got to do the same process, but with the other reactant. So we have to go through this 1 mole of Na2CO3. That is equivalent to 105, so it's not quite as heavy, 0.98 grams of the Na2CO3. Then we need to compare coefficients to go from reactant to product. Here, it's a 3:2 ratio. So 3 moles of the Na2CO3 are going to yield 2 moles of the AuOH3. Last step, which will mirror what we did up here, is getting my reactant back into grams. So for every 1 mole of AuOH3, I will get grams. It's 247.99 grams. Moles of the product are out, moles of the reactant are out, and grams of the reactant are out. So we multiply everything across the top and divide by anything that's in the bottom component. And this tells us that we have 38.99. You may have gotten 40, sorry, not 40. That's where I can round. 39.00 grams of AuOH3. Now that we're both, we have both of them in the product, it's easier to see which one is the limiting reactant. Okay, so the limiting reactant is this. It's the KaUCl4. The excess reactant is this. It's whatever we have, we'll have more of at the end. And then this number over here is known as our theoretical yield. So in theory, if we run this equation through, and we do it very, very efficient to 100%, we could produce 13.12 grams of the AuOH3. Any questions on that hot mess of a problem? They take a while, okay? So as far as a test is concerned, you know, I'm not gonna give you 16 of these to do. I may give you a part here, a part there. You may have one start to finish that's worth a little bit more points than the other ones. Let's do some more on that page. There's a couple other things that I want us to work on. So this one goes into a little farther. It says how many grams of the excess reactant reacted. We don't need to do that. How you would do it, how much of the excess reactant is, you know what the limiting reactant is, right? So you'd go from grams of this into grams of this. And then to figure out how much reactant is left over from the excess, you would subtract it from its original amount. But we're not going to do D and E. This is what I want you to do right here, F. So what is the percent yield if in theory or in actuality you only produce 9.848? 9.848, 9.848. 9.848 grams of the AuOH3. This is your actual. Okay, I want you to find what is your percent yield. How good were you at running this experiment if you could only produce 9.84 grams? So That one I'll just give you like 2 minutes. You don't need a whole lot. Okay, so percent yield, it's a real simple equation. Actual over theoretical times 100, right? A over T times 100. A before T in the alphabet. So actual will be given. This is given to you. Sometimes the theoretical is given. Sometimes you have to solve it through the stoichiometry. So actual 9.848 grams. And then theoretical, where is that? Well, that's sitting back up here in what you solved. So it's 13.12 grams. And because it's a percent, we'll multiply this value by 100 afterwards, or move the decimal over 2 places. So 9.848 divided by 13.12. And we get 75. And I'm gonna go with 4 sig figs. So 75.10%. Questions on percent yield, actual over theoretical? Pretty easy. That's kind of refreshing after the previous section. Okay, let's see. Really, we're just gonna practice this. So let's see what ones I have. Leave that one for you. I'll make one. I'll make one up. We can work together on. So I'll type it up. Okay, so we have 18.3 grams of aluminum combined with 27.6 grams of O2. What is the theoretical yield of the aluminum oxide? What is the limiting reactant? We'll start there. And I'm not going to give you the balanced equation, so you make the balanced equation. I'm sure you've got it in your notes somewhere. Otherwise, you can figure it out. It's aluminum plus oxygen gives us aluminum oxide. I'll give you all 10 minutes for that first one. Again, if you have questions, please ask. Okay. So the first thing that needs to happen is a balanced equation. I'm just giving you guys a little extra practice for the previous chapter. So we've got aluminum, and it's combining with oxygen, and oxygen is a diatomic, to produce aluminum oxide, which is Al2O3. Aluminum has a 3+ charge, oxygen has a 2- charge, so flip-flop. I'll put a 2 here, a 3 here, and a 4 here. So now we need to start going through our stoichiometry. So the first one is what? We have 18.3 grams of aluminum. I need to convert that into moles. 1 mole of aluminum for 26.98 grams of aluminum. Then we need to go from here over to here. So it's a 4:2 ratio. So 4 moles of aluminum for every 2 moles of the aluminum oxide. And then the last step is to go from moles of our product into grams. So 1 mole of Al2O3 weighs 101.96 grams. Sometimes people will say, oh, but there's 2 of them, so shouldn't I put a 2 here? No, use the coefficients only in this middle step. Don't apply them on the sides. So those will cancel, cancel, cancel. And this first thing is giving us a number of 34.6 grams of the aluminum oxide. You have to run through the same thing, but do it for oxygen. So 27.6 grams of O2. For every 1 mole of O2, we weigh 32 grams. Why? Because it's a diatomic. Treat it as a molecule. We're going to go from oxygen into our product now. So 3 moles of O2 are going to yield 2 moles of the Al2O3. Last step, 1 mole of the Al2O3. This mirrors what we have here. 101.96 grams of Al2O3. So once you've solved for the molar mass of the product you're going towards, you can just reuse it in the second one. This one tells us that we get 58.6 grams of Al2O3. So the limiting reactant is going to be aluminum. The theoretical yield is this thing over here. So in theory, we can produce 34.6 grams. Now let's say that your actual yield is 33.95 grams of Al2O3. Find the percent yield. I'll give you just a minute for that. All right, so percent yield A over T times 100. So our actual 33.95 grams Our theoretical was the 34.6 grams, times it by 100. In this case, we get 33.95 divided by the 34.6. It's pretty close. Times 100, we get 98.1%. So whoever ran this experiment was pretty efficient at doing it. Questions on that? Hopefully after we do a couple of them in a row like that, it starts to make sense. All right, so that's all I've got for you today. If you have any questions about the last 3 chapters, or if there's anything that you want to go over, will totally help you out. Okay? But formally, lecture has finished. So good luck with the exam. Have a good weekend. See you next time. Bye.
Hey, can I get some help for experiment 9? I'm